Hello, in this video we will talk about exponential random variables. So exponential random variable is a continuous random variable. So it can be modeled random variables for the positive number. So if a continuous random variable has a probability density function of this type, so if x small letter f, which means density, probability density, if it is only for the positive number, has lambda e minus lambda x in the power. So if I have this expression for the positive number, so we say this random variable is an exponential random variable. And for the continuous random variable, what we can calculate the probability is to use integral. So for example, if we want to calculate the cumulative probability for exponential random variable less than a particular value. So here x is a particular value. So if we want to know this random variable less than this value, then we can use integral from 0 to this value, and the expression is exactly the same probability density expression. Then take integral over this variable. And the result is 1 minus e minus lambda x. If, for example, x is 3, so cumulative probability, we use the large alphabet. Fx equals 1 minus e minus lambda times 3. So here lambda is a scalar value. And if we in the later page, we know that lambda actually is the reciprocal of the mean of exponential distribution. So the exponential distribution often model the time until next occurrence. So for example, if we model until next specific event occurred time, or until next war come, until next earthquake come, until next failure of instrument, of the battery, of the light bulb, like this. So it is only to model the next one-time occurrence, not a several-time occurrence, only one time. So if we want to find the mean and the variance of exponential distribution, a random variable, we can use the moment generating function. So if you're not very familiar with moment generating function, you can view the video. We have the video in this playlist for the moment generating function. And the basic idea is that we create a generating function, moment generating function called phi t. And here both t and x are random variable. So exponential of the etx power actually is the 0 to integral to the positive infinite for etx sign with the probability density for the exponential distributions probability density. So you can see if we want to calculate a random variable's expectation, actually we use this random variable's expression times its probability density, then take integral for all the available value, right? This applies to every random variable. So this is random variable, and we use, because here only x has probability density, so we use this expression. Then after some transformation, we can get the result is lambda divided by lambda minus t. Then we take integral first time or second times derivative for the first degree and second degree derivative of this function, then we get these two results. So for the mean of a random variable actually is same as the first degree derivative calculated at 0. So the result is 1 divided by lambda. So this is why the parameter lambda is the reciprocal of the expectation of exponential random variable. And variance is exactly the second degree derivative taken value at 0 minus the square of the expectation. So the result is 1 divided by lambda square. So it's very interesting. The variance of exponential random variable is exactly the square of the mean, right? And the most important property of exponential random variable or the exponential distribution is that it is memoryless. What is memoryless? Which means if the instrument, for example, has been used S time, and what you want to know how much more time of the t it can be used. If it has used t, if it has used S, right? So here is the, if it has been used t time. So what is probability of it can be used S time further? It is same as we do not care about how long it has been used in the t. Just calculate the probability of x larger than s. So it is like a memoryless. So we do not need to know the information of t. So say if you have a light bulb, you have used 3 months, and you want to know how long it can be used until the first failure. So this is same to say that you just bought this light bulb and use from now. You do not care these 3 months. So it is a memoryless, or we say the young forever distribution. So next we take a look at an example. Suppose that a number of miles such a car can run before its battery wears out is exponentially distributed with an average value of 10,000 miles. So here lambda is 10,000. If a person desires to take a 5,000 mile trip, what is the probability that she will be able to complete her trip without having to replace her car battery? And what can be said when the distribution is not exponential? So because in the first question, we know that it is exponentially distributed, so it is memoryless. We do not need to care about how much miles this battery has been used. We just used the mean of the battery. We know is 1 of 10, right? So the desired probability of this random variable larger than 5. So here 5 means 5,000 is 1 minus F5. So F5 exactly is the probability that this battery has come to first failure less than 5, right? If we look at the first page, so this is fx, which means the probability of x less than x. So this is a particular value. So for the car's batteries example, which means the probability of this random variable less than 5, right? So if we we just use this expression, right? So we can get because here we want to know the lifetime larger than 5. So we use 1 to minus F5. Exactly this expression is about 0.604. But if the lifetime distribution f is not exponential, so the probability of lifetime, we can use 5,000 miles more which depends on how many miles the car's battery has been used. So we have to use the conditional probability of lifetime now currently larger than t. We have used t miles. Then we use 5,000 miles more the probability. So this is a conditional probability. It equals, this condition is 1 minus ft. We have used t miles without problem. Then next is we use 5,000 miles more without problem, right? So in this case, we have to know the distribution of ft. If this is not exponential distribution. So if it is exponential distribution, it is a memoryless. If you use this expression further, we use the f expression for the exponential, then we will get these results. But if it is not exponential, it will not get these results, right? Thanks for watching.